So before I start, does anyone in the room, by any remote chance, run hydrodynamic simulations in astronomy? So we've got one person, and as long as you don't argue with me, I can make whatever outrageous claims I want. All right. So I'm going to tell you a little bit about a project that I've worked on called YT, which is an integrated science environment for astrophysical simulations. The image in the background is an astrophysical simulation, one of mine, in fact, of a population 3 star forming. So I run deeply nested adaptive mesh refinement simulations of the formation of the first stars in the universe. But that's not really what I wanted to chat about. I knew that I was going to be speaking before a whole bunch of observers, and so I wanted to sort of position this. There's really only one sky, but we have many, many different simulation codes. And in fact, the idea here is that it's sort of the inverse of the story of the Tower of Babel, in where everyone spoke the same language and tried to build, upwards. We've already built upwards, even though we all speak different languages in the simulation community. They all have different methods, so methods of discretizing the fluid, methods of solving the gravity, methods of doing subgrid solvers, how do you handle star formation, on and on and on. They have different data structures, such as, some evolved based on a tree, others have octrees, there's patch-based, block-based, on and on. Assumptions about the way that fluid flows, I/O methods, units, variable names, and so on and so forth. And so really, what we want to do is we want to make a comparison of apples to apples, but for the most part, we end up having to make a comparison of apples to pineapples, something that sounds similar but tastes very different. And so the place where we start inserting these accurate comparisons would be at the level of the analysis phase. And in fact, the YT project, and I've put up here an AstroPH link to the method paper, as well as the homepage of the project itself, and I'm sure by looking at the hit counts, I'll be able to tell whether or not anybody hit that website now, which looks something like this, so you don't need to go there. And we have documentation and so on and so forth, is a project that we've designed to try to bridge this gap. It comes with an install script, so it's odd that James talked about this earlier, but we do try to deploy on all of the NSF resources as well as home computers and desktop machines and so on. And so the install script provides things like the full dependency stack, source code, a full development environment, a GUI, and sample data. And in response to Professor Bloom's question, we do use virtual ENV in here, but we don't use it for the installation process. But on its basic level, what we've done is we've tried to design YT to address physical entities rather than computational entities. As an example, here is an image of a population 3 star forming disk. In the center, you can see there's a protostar. There's what looks like a clear disk forming from it, which is actually molecular hydrogen. But the computer actually sees this as a series of grid patches. These grid patches overlap. If you look closely, you can see that they have different size of resolution elements. And so what we want to do is we don't want to have to deal with grids that overlap, data that needs to be removed, masked, converted into units. What we want to do is we want to deal with things like disks. The universe is full of gas, dark matter, and stars, and we try to make it easy to access that material rather than putting up a whole bunch of barriers in terms of I/O and in terms of other things. Things like, well, the things that I just listed. One thing that I wanted to emphasize is that we do provide things like geometric selection, but we also provide something like field generation. This is probably very familiar to observers. For instance, my simulations involve the density of molecular hydrogen. But for the most part, what I'm interested in is the fraction of molecular hydrogen. And so what we do is we provide a transparent mechanism for a fully functional workflow of taking in the quantities on disk and then outputting meaningful quantities that are some combination of those fields on disk. In this case, it would be the molecular hydrogen density divided by the total density. We support a number of different codes, including ENSO, which is the code that I do most of my work with, Orion and Castro, which are based on the same underlying library, Flash. And then we also have a number of affiliated codes that don't really, or I'm sorry, not affiliated codes, but second-tier codes that we do support, but that don't reach to the same level, such as Chombo, Tiger, Athena, Art, Ramses. And it's designed to be a lingua franca, so you can speak to it in the same language, and then you get out meaningful results that can be directly compared. In addition to that, the idea is that there can be direct technology transfer between users of different codes, whereas previously this wasn't possible because they would have a number of different machine logic spread out throughout their algorithmic implementations. So I'm going to skip most of the object stuff, but the idea is that we provide geometric objects which are conceptually the same. They're uniform access style NumPy stores. Things like orthogonal rays and non-orthogonal rays. So you can provide queries between two different locations in your simulation. Slices through the domain, oblique slices, projections, spheres, rectangular prisms, and so on and so forth. So the idea is that if you can describe it in terms of geometry or in terms of some sort of quantity that the system can evaluate, you can access it and then on top of that, develop meaningful semantically aware analysis. So for instance, you could select a cylinder that encompasses the entire region of a disk galaxy in your calculation, and then have YT analyze the angular momentum vector. In the background, what it will do is it will read in all of the data, mask out overlapping regions, and then provide a result back to you. I'll talk in a moment about parallelism, but that entire process is transparently parallelized using MPI. So as an example script, if I have a galaxy data set, oh, and it looks like my plug is coming undone. There we go. There's the syntax highlighting. So this is an entire simulation, or an entire YT script. We load our data off disk. We create a slice plot of density through the center of the domain along the second axis with 200 kiloparsecs on a side. Now what you may not realize is that in the background, Galaxy 0030 on disk is actually stored from 0 to 1 in terms of its coordinates. And what it's doing is it's converting it to kiloparsecs. We save it out and we get an image like this where the units have been converted to grams per centimeters cubed from whatever internal units the code has evolved. We can also zoom in so that we can go to 20 kiloparsecs and we can look at the disk galaxy a little bit more close up. And then we can do the same thing with projections where we take a line integral through the entire domain of the simulation. And in this case, it'll change the units correctly. One of the things that we get asked about quite a lot is about volume rendering. So volume rendering hydrodynamic simulations is actually one thing that we've added in the last couple of years. This is a Planck transfer function applied such that density governs the level of emission and temperature governs the color of emission to a simulation of a population 2 star forming in a protogalaxy. And it's designed around the idea that we're actually just integrating through a volume, and visualization is a side effect. In fact, what we do is we evolve the entire radiative transfer equation in the absence of scattering, and then that's what's returned to the user. In order to get things like shells and so on, we just apply Gaussians. This is a simulation of a dwarf galaxy forming around redshift 20. These are dwarf galaxies forming around redshift 8, again with the Planck transfer function, where we have color governed by the temperature and emission governed by the density. These are also transparently parallelized, and we also now have a planetarium backend, so you can feed in the field of view of the planetarium that you want to render it on. It'll output a volume rendering in that field of view in the standard format used by planetariums. However, this is also used for quantitative analysis. So this here is what I guess Jake referred to as a bin statistics, where it's the distribution of mass as a function of two different variables. And in the background is an isocontour plot of one of my simulations. And what I like to do is I like to draw out different regions using the volume rendering engine in order to analyze chemical stability. So in this case, I've identified a kink in the equation of state. I've drawn out that isocontour, and I go on from that. We provide a number of canned analysis tasks, such as absorption spectrum, level sets, star analysis, two-point analysis, so on and so forth. Like level sets, this is that same simulation again, where we've identified topologically connected sets across refinement boundaries, synthetic spectra, and two-point functions for things like turbulence studies. A couple different halo finders. Rockstar is the one we're going to focus on because we'd like to outsource that particular functionality. And documentation for all of the analysis modules is available online. So parallelism, just because I know that that has been a topic in this particular classroom throughout most of the day. We have multi-level parallelism, including dynamic dispatch and worker queues, communicator subgroups, and so on. And we can decompose nearly every single one of our operations in an embarrassingly parallel fashion for great scaling, such as quantities, profile slices, projections, volume rendering. And the only one that we're still really struggling with is halo finding, which still needs to be spatially decomposed. Since this has come up a couple times, I wanted to chat about developing as a team. This last January, we had a workshop at the Flash Center where we brought in a number of different students. It was NSF funded, and we had a 3-day course on how to use YT. I know we have a representative from the Flash Center here, so hello. Thank you very much for your hospitality. We have a 4-key development style with a very low barrier to entry. Everything comes in the box with a number of different helper functions. We have integration tests that get run every 30 minutes. And since this morning John Hunter talked about the OLO stats, we've had about 6,000 commits by 34 contributors over the last 6 years or so. I don't buy their estimate of usage of time to recreate. We've got about 80,000 lines of code. And here's a fun stat. This is a punch card. So you can see that at the time this punch card was made, YT was mostly developed during the workday. But there are also some outlying commits made at, say, Thursday at 5 a.m. and Saturday at 4 a.m. And I really need to have a chat with those developers. Just to conclude, I wanted to chat briefly about future directions like exploration. Fernando and I have been talking about web GUIs. We're going to start integrating our existing web GUI with the IPython notebook very soon. But we have a web GUI that contains a number of different widgets and so on. But I actually have a demo of that GUI running on the Gordon supercomputer at SDSC. And so what we can do, running with no additional dependencies outside of what comes in the box, we can explore very large data sets on remote systems. It's going to take a second for it to do that and come back. But anyway, let's go back here. I know that my time is running short, so I will attempt to finish up. But with a number of different widgets and so on, including recently added a 3D scene graph widget using XTK, a library out of Harvard Medical School. We're working on collaboration around things like transient data objects like projections and so on. And so we've actually built up a very simple Google Maps interface. This is running remotely on Amazon's cloud. And you can zoom in, and it's regenerating the images as we go around. And we're hopeful that this will become a platform for collaboration between users from different groups. We're working towards tighter integration with simulation codes, as well as an I/O library and moving from grids to chunks. But the reason that I'm skipping here is because I wanted to share something that happened very recently. We're working hard on YT as a platform for outreach. And specifically, we're working on this as a Trojan horse for outreach. We've put this in the hands of many different simulators, and what we'd like to do is make it very easy for those simulators to provide short-form material for planetarium. Long-form material is a completely different story, and we're not aiming for that market, but there is a space for short-form material. And in fact, play the movie. This is a movie that we supplied recently using all of the same tools that we use for analysis and publication. This is one of my simulations, and it'll transition to a simulation from another one. This is a movie that we provided to the Adler Planetarium recently that made it into one of their galleries. It's going to take a second as it zooms outward. And of course, there are things that I would like to improve about this, but at the same time, I'm just delighted that we were able to use the same tool that we use for publication to provide short-form visualizations for outreach quality materials. And then it pauses for a second, and then we actually see some time series data also visualized with the same toolkit. This is a population 3-star exploding in a pair instability supernova after it lights up and ionizes its surroundings. These simulations were run with the simulation code ENSO and then visualized later on using YT. And actually, this is by far not the most beautiful thing that I have from this particular simulation. The most beautiful thing, which I'd very much like to show you, is this. This is probably staged by the Adler PR, but I still think it's amazing that they put this photo up of two little girls looking at our simulations and hopefully being inspired by science. So here is a list of the contributors, and I've highlighted in bold those contributors who are who have either contributed a large portion of code or who may be looking for jobs this fall. And thank you very much for your time. Well, so the problem with Gadget is that it's like 1,000 codes, right? Each one with its own I/O format. We're working on Gadget support, and I'm optimistic that, and really I mean it this time, by the end of the year we'll actually have meaningful support for Gadget.
Would this lend itself to distributed processing, borrowing cycles from the computer
Well, I guess one of the problems that we would run into there is that the latency is very high compared to the number of cycles that we want. We're actually, right now, very interested in low latency communication compared to the number of cycles. Thanks, everyone.